of Europe. So it's my pleasure to welcome Helen Innes from the University of St. Andrews. Helen's a postdoc there and is working on ice core petrochronology. And with that, I'll hand it over to you, Helen. Thanks very much.
Sure, thank you very much, Ray. So hi everyone, I'm Helen. As Ray says, I'm a postdoc at the University of St Andrews in Scotland, in the School of Environmental Earth Sciences. And thank you for inviting me to talk today about this paper from my PhD that I did with my lovely co-authors listed here, where we examine the evidence of the Los Chocoyos supereruption and what this evidence tells us about the climate significance of the supereruption. So first of all, I'll just start by bringing us all up to speed about why we care about explosive volcanism and the impact that it has on climate. And this figure from Marshall et al. In 2022 does a nice job of kind of explaining all the processes and impacts that are happening as a result of this volcanism. So we have the very explosive event here, and it emits lots of gases, including sulfur dioxide, and lots of ash. And in the atmosphere, this sulfur dioxide condenses to form sulfate aerosol, and that aerosol is what's important in reflecting and absorbing this incoming solar radiation. This causes cooling at Earth's surface, and if we have a particularly explosive eruption and this plumes in the stratosphere, then that aerosol has a really long residence time of 2 to 3 years, allowing it to be transported globally and causing the scattering of the incoming radiation to occur kind of for 2 to 3 years following the eruption. Whereas if the plume is only tropospheric in altitude, then a lot of that aerosol is removed from weather processes in the days to weeks following the eruption. So it's these really big stratospheric eruptions that we're interested in terms of climate forcing. Also of interest in this figure is in the corner here, just this little bit about ice sheet deposition. So when that sulfur aerosol is deposited out of the atmosphere and it lands on the ice sheet as kind of preserved in the snow and ice, we see the sulfate aerosol preserved as peaks in sulfur going back through time in the ice core. And this is kind of our best record of volcanism going back in time due to the well-constrained age models of polar ice cores. And we can use these ice cores to reconstruct volcanic events, understanding more about their radiative forcing from the sulfur aerosol quantities that are deposited there. We can see how these explosive volcanism events impact climate by looking at these ice core records. So this figure from Sigel et al. 2015, demonstrates the relationship between when these volcanic events are occurring and the cooling impact that we see at Earth's surface. So the bottom panel here, this is from that ice core record that I was describing, where we can see large peaks in the sulfur concentration, and we know that these events are happening, and we can get some idea of the aerosol forcing from that eruption. When we compare the timing of these eruptions in the ice core record to a temperature proxy, so here it's tree ring records from the Northern Hemisphere that are annually resolved, we can see when the coldest years of the last few thousand years were. So here we can compare, for example, the 1815 eruption of Mount Tambora, which is responsible for the 1816 year without a summer. We can see the low temperatures reflected in the tree ring proxies from the Northern Hemisphere, where we see some of the coldest years of the last few thousand. Other periods of time, such as the Little Ice Age in the early 1600s, is coincidental with a sequence of eruptions in the 1600s, and also a cluster of very cold years and decades in the 540s is started by these couple of very large volcanic events here. So this, by combining these ice core records with temperature proxies, we can really see how these eruptions are causing cooling in the years following from that stratospheric sulfur injection. Thinking about the wider climate system as well, so we can look at, so this is a modeling study that modeled an 1809 and 1815 climate system responses. First of all, if we look in this top figure here, we can see when eruptions were modeled as occurring with the dashed line. And this is for air temperature, so we can see a decrease in air temperature following these eruptions. But in the bottom graphs, we see how the wider climate system responds to that cold temperatures. So when we have the big volcanic events, we get an increase in northern hemisphere sea ice cover and also changes to the way that the heat is transported in the oceans. So not only do we have volcanic events, but we have these climate feedbacks, which can prolong and exacerbate the cooling that is triggered initially by that big injection of sulfate to the stratosphere. But I'm here to talk about super eruption today. No super eruptions are known to have occurred in historical times. So these models are of the largest eruptions we know to have happened in the Common Era or historical times. So what is the impact of eruptions even greater in size than these ones? Well, first of all, what is a super eruption? How do we define that? Super eruptions are at we define a supereruption as being at VEI 8, so that's on the volcanic explosivity index scale, at 8 or greater. And this is 10 to 100 times greater in size than eruptions from the historical era, which the largest of which, like Pinatubo, Tambora, etc., are VEI 6 and 7. The scale is based on erupted volume and it's logarithmic scale. So with the VEI supereruptions that are VEI 8 supereruptions are 10 to 100 times greater than anything we know to have happened in the last few thousand years. And we need to, as well as the volume of rock erupted, we need to consider whether these erupted a lot more gases or not than the Common Era eruptions. In the last 100,000 years, we know of 4 eruptions that have been large enough to be classed as supereruptions. That includes the Los Chocoyos eruption of Atitlan, which is what I'm going to be talking about today. And we also have the younger Toba Tuff eruption of Toba in Indonesia, ASO 4 in Japan, and the Oronui eruption of Taipo in New Zealand. But as I said, what impact do these supereruptions have on climate? And that's something that has historically been discussed and debated slightly. So the worst case scenario is that the supereruptions have been linked with triggering major ice ages. It suggested that this mass injection of sulfate to the stratosphere may trigger cold conditions, which the feedbacks of which kind of exacerbate it and continue it, prolonging this ice age. And this theory is kind of underpinned by the timing of one of those supereruptions, the Toba supereruption. And the timing, the date of that eruption is coincidental with when Earth is plunged into a stadial period, a really cold period. And that's kind of where this theory comes from, as well as potential theories that the Toba eruption caused a human population crash or a genetic bottleneck. However, studies which have modeled extreme injections of sulfur to the stratosphere, several times greater than common era eruptions, suggest there is actually no glaciation link, such as this paper here from Timmer et al. 2010, which modeled a supereruption, younger Toba Tuff size stratospheric injection. They show that, yes, there is this extremely large cooling, short and sharp in the years that follow the eruption, but slowly the climate state returns to normal within almost a decade. It's almost back to pre-erupting conditions. But how can we test this theory? We need to look at real events and real climate records to really understand what the impact on climate was from these supereruptions. And for this talk, I'm going to focus on the Los Chocoyos supereruption of Atitlan caldera. This is the largest eruption known from the Central American volcanic arc, and it's one of the largest quaternary eruptions. The tephra deposit from this eruption can be found up to 2,000 kilometers away from the site in all directions. So there are several sediment cores in the Gulf of Mexico, the Caribbean Sea, and the Eastern Equatorial Pacific that contain quite a large tephra deposit in them, demonstrating how kind of powerful this eruption was and how much material was erupted from it. In terms of its age, there has been a lot of interest in Los Chocoyos since maybe the 1960s, with lots of people proposing dates from different methods. This date of 84,000 years was widely accepted since 1980, really. And and it's determined from a marine sediment core in which there was a good oxygen isotope stratigraphy date for the ash. However, more recently, there has been radioisotopic dating of zircons from the eruption, and this gave a younger age, slightly younger age of 75,000 years for the eruption. This date is important because it makes the eruption younger, and as pointed out in Payne et al. 2021, this puts the Atitlan Los Chocoyos eruption within dating uncertainty of another supereruption, the younger Toba Tuff, and it puts both eruptions within dating uncertainty of a major climate shift to cold conditions known as Greenland Stadial 20. We can see these warm and cold periods going through Earth history from looking at ice core temperature proxies. So that's what this figure from Payne et al. Here is the Greenland ice core oxygen isotope record, which shows warm and cold periods going back in time. And the warm periods are shown as these elevated isotopic values, and the cold periods are shown as the more negative values. So the period we're interested in is this 75,000 year kind of roughly time here, where we have potentially two super eruptions occurring and then transition to this particularly severe cold period known as Greenland Stadial 20. So this paper raises the question, could this sulfur injection from back-to-back super eruptions trigger glacial conditions? Is it this two major sulfur injections that is sustaining the cold temperatures and pushing us into ice age? To test this theory, we first of all investigated evidence for the timing of the Los Chocoyos eruption. So first of all, we have that radioisotopic age of 75,000 years that was published in 2021 from dating of zircons. And then we have also the marine sediment age that was previously adopted of 84,000 years. Now, because this date was published in the 1980s, since then there has been revisions of the marine isotope stage dates and improvements of age records. So actually we can revisit this and see if we can improve on the marine sediment age for the eruption. So as I mentioned earlier, the Los Chocoyos eruption erupted huge amounts of material that covered the entire kind of Central American, Gulf of Mexico, Caribbean Sea region. The ash is therefore found in many sediment cores. This is the sediment cores that it was found in 1980, and since then it's been identified in many, many more. And of particular interest is this core, V1929, and this is the sediment core that was used in 1980 to give the eruption the date of 84,000 years. The reason this could be done is because V1929 has a lovely benthic forum oxygen isotope record, which records the sea level through time, and this curve is similar throughout, this curve is similar globally, so the ages of the highs and lows within this are well constrained. This means that the position of the ash, which at the time of this was only known as ash layer D before it was correlated to Los Chocoyos, they were able to give this ash a date of 84,000 years based on its position in this oxygen isotope stratigraphy. Interestingly, we noticed that about 50 kilometers east of V1929 is the core V1930. And V1930 is a similar sediment core, which has a benthic oxygen isotope record as well. However, the record here is much higher resolution than V1929. It's in fact one of the highest resolution records in the region that's been used in multiple other climate studies. So this would be ideal if we can locate Los Chocoyos ash in this core, then we would be able to greatly improve the timing of the eruption. So luckily we have a guide of where the ash might be. We've got, we know in the V1929 stratigraphy where the ash is. So we targeted this, this stratigraphic position and sampled V1930, identifying volcanic ash in a kind of 3 centimeter horizon of that core. We then cleaned and prepped the ash, analyzed it using electron probe microanalysis for major and minor elements. And because we wanted to see if it matched Los Chocoyos tephra, we also got proximal Los Chocoyos ash and analyzed that alongside our alongside our sediment core shards to see if they matched. And when we compared them, we saw a beautiful correlation. So the blue points are our proximal Los Chocoyos analysis, and our red triangles are the sediment core tephra that we analyzed. So we were happy that we had found the Los Chocoyos tephra in V1930, and we can now use this to try and better improve the marine sediment age for the eruption. So as promised, this is the oxygen isotope record of V1930, which is a high resolution oxygen isotope record from the region. And we can see all the marine isotope stages labeled here, and the highs and lows through the last kind of 140 years, 140,000 years or so. And because these highs and lows in the marine isotope stages are similar globally, they're well dated, and we can apply an age model to this record. So we use the LRO4 stack, which allows us to look at the position of the Los Chocoyos ash in this core and assign it an age of 80.5 thousand years. Now, because the marine isotope stages are similar globally, we can also do an interesting experiment and compare the timing of the Los Chocoyos ash in the Eastern Equatorial Pacific with a core that the Toba ash has been identified in the South China Sea. So these are two separate cores with this top one has the Toba ash and the bottom one has the Los Chocoyos ash. But because of this oxygen isotope stratigraphy, we can compare the relative position of the tephra in each one. And in doing this, we can show that there is a clear separation in timing between the Los Chocoyos eruption and the younger Toba tuff supereruption. In this, it suggested it's about 5,000 years, but you can see that the Los Chocoyos ash appears at this high point in marine isotope stage 5.1, and the younger Toba tuff is much closer to this transition between marine isotope stage 5 and 4. So by doing this, we can rule out the possibility of a closely spaced doublet supereruption. So back to our ages, we can update this marine sediment age to 80.5 thousand years, making it slightly younger and closer in age to the radioisotopic age. And finally, another way to date a volcanic eruption is to identify the evidence in polar ice cores, which themselves have very well resolved age models. And that's where this next section of the talk is going. So, as I mentioned in the introduction, ice cores record volcanic events as peaks in sulfur aerosol, and sometimes any ash or tephra that reaches the ice cores as well. This is kind of a typical example of an ice core record of sulfur, where we see these big peaks corresponding with large volcanic eruptions, and occasionally accompanied by volcanic ash that has also been found. The volcanic ash is key for linking the deposit in the ice core to a volcanic source. The only way that we can say with any certainty that a deposit is from a volcanic event is if we can geochemically analyze the ash in the ice core, and this is essentially its fingerprint that can then be matched to a source eruption. So that's what we're trying to do here to identify Los Chocoyos in polar ice cores. But first we need a candidate, and looking at Greenland and Antarctic ice cores, there is a very large peak in sulfur concentration at 79.5 thousand years on the Antarctic ice core chronology age model. This sulfur peak is particularly large. It's one of the largest for the last 100,000 years, so a perfect candidate for a super eruption-sized event. So could this be Los Chocoyos? And yeah, this age is in perfect agreement with our sediment age. So again, a good candidate. And it's also worth pointing out that there is a separation of approximately 5,000 years from the younger Toba tuff candidates. So I should specify that the Toba eruption's not been identified for certain in the ice cores, but studies have shown that these are the most likely candidates for the other large super eruption, the younger Toba tuff. And this separation of about 5,000 years is similar to what we see in sediment cores. So we sampled those two ice cores, one in Greenland and one in Antarctica. So we actually sampled the Neem ice core in Greenland and the EDC ice core in Antarctica. And what we do is instead of sampling one big piece of ice across the whole eruption, we do high resolution sampling. So taking multiple small bits of ice across the deposited peak. And this means we can analyze the sulfur concentration there and see how that evolves through time. And when preparing tephra samples, we can prepare each sample individually, allowing us to pinpoint the exact timing of any volcanic ash relative to the sulfur growing in. And this is how we prepare the tephra. So we dry down each ice core sample, and then we mount any dust that's present in the ice core in an epoxy resin mount ready for analysis with SEM or EPMA. One of the reasons why the high resolution sampling is so useful to us and being able to pinpoint the timing is that for large tropical eruptions appearing in ice cores in the poles, we expect the tephra to arrive immediately prior to or during the initial growth of the sulfur aerosol. And this is just simply because they're both being transported through the stratosphere, and that tephra is going to have a slightly greater settling velocity than the sulfur aerosol, so we're more likely to see it immediately prior to or with the initial sulfur deposit. In our samples, the ones we analysed our samples first with an SEM to look for any ash shards that were there and to check there was anything worth analysing. And all the samples highlighted in grey here at the top are ones in which we found 2 or more tephra that had the same geochemistry, so that classes it as kind of population. So we performed analysis on these tephra shards and compared them to candidate geochemistry, so again to the Los Chocoyos proximal ash. And we found that we had 3 shards in the Neem ice core that were in Greenland that were consistent with Los Chocoyos geochemistry, and 2 shards in Antarctica that were also consistent with Los Chocoyos geochemistry. So by identifying these shards that correlate across all major oxides with Los Chocoyos ash, we have the best evidence for the Los Chocoyos eruption in both Greenland and Antarctica, to suggest that this sulfur peak in ice cores is from Los Chocoyos. So that allows us to assign an ice core chronology age of 79.5 thousand years to the Los Chocoyos eruption from the dating in the ice cores. So we can add that age into our list of various Los Chocoyos eruption ages, and we now have 3 independent ages for Los Chocoyos that are consistent, suggesting that the eruption occurred around about 79 and a bit thousand years ago. But I'm first going to cycle back to this zircon dating for Los Chocoyos, as since our work on Los Chocoyos and our paper was in review and now published, there's been further developments and discussion that have presented themselves that are worth touching on just a bit for the purposes of this talk. So this is the original date for the zircon dating from Cisneros de Leon et al. 2021, where they analysed zircons using uranium, thorium, helium analysis, giving us this 75,000 year age for the eruption that started the debate about whether it was related to the Greenland Stadial 20. Interestingly, since this, there's been further zircon and plagioclase dating that has been published, suggesting that Los Chocoyos was actually much older. This study, published by Baudry et al. 2024, uses Bayesian eruption age modeling with the zircon and plagioclase dating to determine an age of 98,000 years for Los Chocoyos, which is all the kind of colourful lines here around about the 100,000 year mark. And this is much older than so this is the previous oxygen isotope sediment eruption date and the newer Cisneros de Leon zircon dating of 75,000 years. First of all, it's worth noting that both of these data sets include data which is very disperse and has large uncertainties. This is what we can see in this plot here. So we've got a range of data points of 40,000 years, all with quite large uncertainty bars. And statistically, processing this data requires major assumptions to be made, such as the reasons for the dispersion and also zircon crystallization ages. And the assumptions that are made here have the potential to impact the outcome of the analysis with potential over or underestimation of eruption ages. So since these studies came out, Cisneros de Leon et al. Have taken all of that zircon data and reanalyzed it all, applying different assumptions to that data. And all that you really need to notice here is that by using Bayesian eruption age models and using different distributions for the modeling, depending on the assumptions you make and the distribution that you use based on these assumptions, you can get quite a variety of dates for the eruption. And so therefore, this study, it also discusses how the dispersion in the data is likely related to crystallization times. And all of this basically just shows that we really need to understand the eruptive processes, the crystallization, in order to make the right assumptions about the data set. But in their paper, the thing that we need to take home is that they show that the eruption couldn't be older than 83,000 years. And they reconfirm their age from 2021, that the Los Chocoyos eruption is about 75 plus minus 4,000 years based on the zircon dating. What this does demonstrate for us is the importance of having multiple ages for eruptions with independent methods. So where the radioisotopic age could be debated, we have also marine sediment core age and an ice core age for the eruption, which agree and therefore can provide additional constraints on the timing of the eruption. But what about the climate impact? Now we have an ice core age of 79.5 thousand years for the eruption. What can we say about the climate impact of the Los Chocoyos supereruption? For that, we are returning to ice core records. And this is where ice core records are extremely useful for looking at older eruptions and their impacts, because alongside the sulfur record of ice cores, so this is the sulfur peak that we identified as having Los Chocoyos correlating ash in it. Alongside these sulfur records, the ice cores also preserve paleoclimate records of warming and cooling. So this is the oxygen isotope record from both Greenland and Antarctica. And in these records, we can see warm and cold periods, again, with elevated oxygen isotopes as the warm periods, and then lower values as the cold periods. And when we look at this temperature record, we see that when the Los Chocoyos eruption occurred, it's occurring in a very stable period of Greenland interstadial 21, and many thousand years before this descent into Greenland stadial 20. This is the cold period that it was associated with. So because we're looking at the sulfur record and the oxygen isotope record at the same depth, we can see a direct comparison here. Sorry. So we can take a slightly closer look at this window here. So when we zoom into the 1,000-year window across the eruption, we see that the eruption actually occurs at a small low in that oxygen isotope record, suggesting that there maybe was a short-term cooling associated with the eruption. But because we don't see a major climate shift, we can say there's no long-term cooling following Los Chocoyos, and any cooling was decadal in scale at most and not millennial. How does this fit with what we know about these large eruptions? Well, this agrees with the studies which model supereruption size stratospheric sulfur injections. This model by Brennan et al. Looks at the temperature following the Los Chocoyos supereruption, and they show that there was severe cooling of about 6 degrees for about 5 years following the eruption, but there is recovery to pre-eruptive conditions within a few decades following the eruption. And this cooling the impact is longer than the aerosol residence time of a few years because of the feedbacks of things like ice and ocean circulation. And I keep seeing in these graphs, I keep saying super eruption size stratospheric injections. What am I actually meaning by that? Well, from the ice cores, we can also use the sulfur deposited there to estimate the volcanic stratospheric sulfur injection, which is the amount of sulfur that that volcano is erupting to the stratosphere. To do this, it's best to use as many ice core records as possible. This is because there's often differences in the amount of deposition or preservation of sulfur at a given ice core site, and therefore using multiple cores gives you the best representation of the sulfur loading. So doing this calculation, we worked out that there's approximately 226 teragrams of sulfur that was erupted from the Los Chocoyos eruption of Atalan. But what does this mean what's the context of this? So we can compare that to large eruptions from the Common Era and look at their associated cooling to understand what kind of impact that might have had. And we see that Tambora is about 10 times smaller and Pinatubo has about 8.5 teragrams of sulfur. And both of these eruptions are still associated with global cooling on a smaller scale than possibly Los Chocoyos. So the fact that Tambora is associated with about 1.5 degrees of cooling gives you an idea of how significant a cooling we might have seen following the Los Chocoyos eruption of Atalan. So that kind of leads us to the question of why. Why don't we see a major climate shift into an ice age following a supereruption? So this is something that definitely is requiring more thought and investigation. Some of the thoughts put forward are that background climate state is very important. We show the Los Chocoyos supereruption occurred during a very stable period of Greenland interstadial 21. And at this point in an interstadial, it's likely that AMOC was very strong, and it might have taken a lot more than a few years of aerosol to completely shut this off and cause ice age conditions. This is what the modeling studies show as well, that although we have short, sharp cooling and big increases in global sea ice area, there is very slow recovery, and the feedbacks don't kind of run away and give us these ice age conditions. Another important consideration is the volcanic dynamics themselves. So looking at the plume, with these really large super eruptions, we have really large amounts of material being erupted from them, and therefore very dense plumes with lots of sulfur, lots of ash. And there's the line of thought that these large eruptions are actually self-limiting. So the more material and the denser a plume you have, the faster you're going to have things happening like coagulation of sulfur aerosol particles. They're going to vary because there's the density of the plume is so great. There's going to be higher collision rates of these sulfur aerosols, and they're going to rapidly increase in size and then fall out of the plume faster. Another factor to consider is the role of ash in this plume as well. And we know that from the deposition of ash across the entire region that Los Chocoyos is very ash rich. And therefore, we need to consider the role of ash in uptake of sulfur dioxide in the plume. And because of the settling velocity of tephra and ash, that ash might be like removing significant amounts of sulfur from the plume before it can condense to aerosol and affect the climate. And this is something that's not considered often in these climate response models. Often they do think about the sulfur aerosol, but the role of ash is something that is definitely requiring more investigation in these climate models. And that takes me on to the summary and take-home points from this work. So by looking at existing data from the existing ages and publications from zircon dating, revising marine sediment core ages, and looking at ice cores for evidence of supereruptions, we can give the Los Chocoyos eruption a revised age of 79.5 thousand years. By identifying the eruption in ice cores, we can look at the ice core temperature proxy records, and we see that there was no long-term millennial scale climate changes following the Los Chocoyos supereruption, despite the 226 teragrams of sulfur estimated from the ice core deposit that was erupted to the stratosphere. And instead, we anticipate that there would be a decadal scale disruption to climate following the eruption. Why don't we see longer term changes? Well, it might be related to self-limitation of these large eruptions and that fast aerosol removal from the plume. Or perhaps there's more resilient climate states to these large super eruptions. And what do we want to do next? Well, this is one such case of finding a super eruption in the ice cores. Ice cores are one of the best archives as we have well-dated records, and we have both the volcanic evidence and the temperature proxy in the same record. Therefore, continuing to identify these big eruptions in ice is of key importance to understanding more about the climate response to large eruptions, and also including things such as self-limitation and ash in these models will help us understand more about what effects the super eruptions have. And that is me. Thank you.
Thank you so much. That was really super.